In this video, we're going to develop a model to describe binary interactions in a solution or a mixture. In contrast to the previous models we developed, which were relevant for dilute solutions and mixtures, here we're going to develop models that are relevant for concentrated solutions. All right? And so, in general, when we think of a solution, to be the most general that we can, we're going to want to account for the non-idealities that arise due to different interactions between the different molecules. And so to describe these interactions, what we want to do is we want to start by considering the free energy of solution. So interactions will affect the free energy of solution. And so we could either take a look at the Helmholtz or the Gibbs free energy. For today, I'm going to focus on looking at the Gibbs energy. But this is going to be an analogous sort of derivation if you wanted to do it with Helmholtz. And so if we think of the Gibbs energy of a particular mixture, we're going to have the summation of the ideal solution Gibbs energy. Then we have the entropy of mixing terms. And then what I'm going to write here is the internal energy of mixing. Now, even though we're dealing with Gibbs, it may seem strange that I'm writing delta U here. But what we have to remember is that by definition, the enthalpy of mixing will be a delta U mixing plus some sort of PV term. We're operating isobarically, so here we would just be looking at the delta V of mixing. Now for the model we're going to develop today, we're going to assume that the A and the B particles in our mixture have the same molar volume, such that the change in volume upon mixing is 0. And so based on that assumption, it turns out that our delta H term is going to be equivalent to delta U. Right? And so that's why I'm going to write delta U in there. All right, and so to describe the free energy of mixing, we need some sort of way to get the internal energy of mixing. And so to develop a model for delta U mix, you want to consider the interactions for a particular model system. And what we're going to consider are the interactions that can occur in a A-B mixture in a lattice. Okay? And so, if we think about the A-B mixture, the type of interactions we could have are between A molecules or between B molecules, or we could have interactions between A and B molecules. Right, so we could rate this one as either AB or BA. It's going to be equivalent. Okay, and so if we consider just the internal energy of the mixture, not the change, but just like if we have the mixture, what is its internal energy? Right, it's going to be a function of the energy of each type of interaction. And so this epsilon is the bond energy. And it's also going to be a function of the number of each type of bond. Move this closer. Okay. And so we could call this the number of bonds. Okay. All right, for a given system, the energy is set by sort of the temperature and the surroundings. But the number of bonds, we want to be able to figure out what those are. Right, so right now those are our unknowns. In order to describe them, we could develop extra equations to describe the number of those bonds. Okay? And essentially, most of those equations will just be material balances. And so in order to figure out the number of bonds that the A molecules are involved in, we could just think of the number of A molecules we have, Na, multiplied by the coordination number, right, which tells us how many sort of bond slots are available for that molecule. Here. And so here, we want to describe the number of bonds that A is able to form. And so for the AA bonds, 2 A molecules are involved. So we'll multiply that by 2. While for the AB bonds, only 1 A molecule is involved. We'll call this equation 1. For the B molecules, we could develop a similar equation. Plus MAB. Right. So far we have 2 equations, but we have 3 unknowns, so that means we need 1 more equation. Right. And so for this third equation, what we're going to do is we're going to make an assumption. Or, in other words, we're going to make an approximation. We're going to apply what's known as the mean field approximation. And so for this assumption, what it is let's say you have an A molecule. Right, we're taking the point of view of an A molecule, and we want to figure out how many B molecules it's able to interact with, or how many B contacts it forms. And so in this approximation, we're going to assume that the number of B contacts that A is able to form is proportional to the probability of B molecules in the entire lattice. All right, so that's the definition in words. In math, we'll just say that MAB is approximately equal to, we have our number of A bonds times Z, so that gives us the number of bonds that A is able to form. And it's just going to be multiplied by the probability of a B molecule in our system. We know that we could describe that probability just by saying NB over N. Right? And so here, I'm going to make a couple of substitutions. For NB, from a material balance, we know that's just equal to N minus NA. And then the other thing I'm going to do is I'm going to multiply the equation by N over N, so multiply by 1. And the reason for doing that is that allows me to rearrange the equation like this. So that now my NA over N, not only is it the probability of A, but I could also express it just as a mole fraction. We're also going to have another Na over N here. And so the number of AB bonds is just going to be Zn x times 1 minus x. And that's going to be our equation 3. All right, and so now that we have these 3 ancillary equations, what I could do is I could apply them together, or combine them, in order to get an expression for U mix. So U mix now is going to be Z epsilon AA divided by 2 Na plus Z epsilon BB divided by 2 NB plus Z epsilon AB minus epsilon AA plus epsilon AB divided by 2 Na NB over N. Okay. Now, once again, these divided by 2's and this equation, that comes from just combining our three equations here. Okay. All right. Now, here we kind of have this long energy term. And to simplify it, what we have to remember is that this energy term is proportional to the temperature of the system, or is related to the temperature of the system. And so I'm going to rewrite this term as kBT, so that accounts for the thermal dependence of the system. And for the parts that don't depend on temperature, I'm just going to call this chi AB. Right? And so that allows us to write U mix like this. Plus Z epsilon BB divided by 2 NB, then plus kBT chi AB NA NB over N. And this chi constant is known, typically called an interaction parameter. Okay. All right, so now that we have an expression for U, what I want to do now is what we actually want, remember, is we want the change in U upon mixing. And so the change in U upon mixing, all right, that's going to be U mix minus U before mixing, where we just have the A molecules separated and the B molecules separated. And so for delta U mix, we'll write the U mix equation we just derived, plus Z epsilon BB divided by 2 NB B over N. Okay. And then we're going to subtract off the premix term. And for the premix term, it's just going to be the number of A molecules times that energy, right? Or A molecule bonds. So to describe that, as we already did before, it's just this. And it's the same for the B molecules. Okay? As a result, these terms cancel. And so our delta U mix ends up just being this term. Chi AB NA NB over N. Or I could rewrite it in terms of the mole fractions. Where this is chi AB. And I'm just going to write X, 1 minus X, to represent the mole fraction of the A species. Okay? And so now that we have delta U mix, I could describe G mix like this. GA plus GB plus N KBT. So here's the entropy of mixing. Oh, let's call this X. Plus 1 minus X ln of 1 minus X plus NKBT chi AB X 1 minus X. All right? And so, we call this delta G mixing, or another way to think of it is it's our excess Gibbs energy. Those are equivalent statements. All right? Now that we have G mix, in the end, what we want is delta G mix, which is just G mix minus G premix. These are our premix terms, and so delta G mix in the end just ends up being this. NKBT X ln of X plus 1 minus x ln of 1 minus x plus x 1 minus x. All right. And so this equation that we just developed, it's known as the regular solution theory. And this is an equation or a model that can be used to describe the Gibbs energy of mixing for, concentrated solutions.